This is the worksheet part 3, and in this part we're going to look at problems 5 and 6 on the worksheet. Both of these are fairly straightforward, so if you have a little bit of trouble, this would be a good place to look. Also, the solutions are online. Okay, 48 Newton force is required to start a 5 kilogram box moving across a horizontal floor. What is the coefficient of static friction between the box and the floor? Okay, let's see. So I want to know the coefficient of static friction, mu s. Okay, the only equation that mu s shows up in is the static frictional force equation, which says the static frictional force is equal to the normal force times the coefficient of static friction. Okay? Which means if I know the normal force, I can find the static frictional coefficient. Okay? But it is a force problem, and that means I want a diagram. Okay, so here's my crate sitting right here on the floor, and it's a 5 kilogram box, and it says that a force of 48 newtons, so this is going to be my 48 Newton force, is required to start a 5 kilogram box moving across a horizontal floor. Okay, and so of course there's force due to gravity, which actually pulls straight down, not at that funny angle I just drew it, and the normal force. And those two cancel each other, and of course there's this frictional force right here, Fs. Okay, and remember, the maximum static frictional force is the force required to start an object in motion starting friction. And so basically, if this 48 newtons this way, I know that the static frictional force is 48 newtons the other way. Okay, and so the normal force is just mg in this equation because gravity is straight down and the normal force is straight up. And so that's 5 times 9.8, which is just 49 newtons. Okay, and so then I'm going to use this equation, static friction, 48, equals normal force, 49, times the coefficient of static friction, divide both sides by 49, and I get the coefficient of static friction is equal to 0.98. Remember, that's a unitless number. It tells me that 98% of the normal force is actually frictional in nature as well. Okay, look, after the box starts moving, a 48 Newton force continues to act, causing the box to accelerate at 0.7 meters per second. What is the coefficient of kinetic friction? Okay, now I'm going to redraw my picture because now I'm looking for mu k. Okay, and so same equation, Fk equals normal force times the coefficient of kinetic friction. The difference is now the box is in motion, and so instead of static friction acting, I've got kinetic friction. Okay, and so those should be touching. There we go. And so this 48 Newton force is still acting, but now we also have the frictional force. However, kinetic friction is a little bit different than static friction, and generally it's a little bit less. So I still got the normal force, and I still got mg, and these haven't changed at all. And so the normal force from above I still know is 49 newtons, and the applied force is 48 newtons, and it says it's accelerating at 0.7 meters per second, 0.7 meters per second squared. Okay, Newton's second law says net force equals mass times acceleration. Well, the net force is that 48 newtons that's being applied to the right minus the frictional force, Fk, and that equals the mass of the box, 5, times its acceleration, 0.7. So now I have 48 minus the frictional force equals 3.5. And I'm going to subtract over the 3.5 and add over the Fk, and I get the frictional force is equal to 30, or not 30, 48 minus 3.5, which equals 40, what does that equal? 44.5 newtons? 44.5 newtons. Okay, not the answer to the problem. That's just Fk. Okay, I'm going to take Fk and divide it by the normal force, 49, to get the coefficient of kinetic friction. And this equals about 0.91. And again, no unit, it's just the coefficient of friction. Okay, so pretty straightforward problem there. Just know the difference between kinetic and static friction, and remember Newton's second law is net force equals mass times acceleration. This last problem is long looking, but it's got no math involved in it at all. It just wants you to pay attention to how forces change when motion changes and how to deal with forces on an incline. So I'm going to have a decent looking incline for a change, because I'm going to cheat when I draw it. So there's my incline, and I've got an object sitting on it. Okay, draw a free body diagram showing all the forces acting on the box if it's at rest on this incline. Okay, so here's my box resting on the incline. And now I just need to label my forces. Okay, I always start with gravity. Okay, and gravity always pulls straight down. So this is Fg. Okay. Then I generally label my normal force, because if it's sitting on a surface, there's a normal force there. But remember, the normal force does not push against gravity. The normal force is exerted by the surface on the object perpendicular to the surface. So the normal force is at an angle. Okay? And it says this is resting here. If it's resting, that means that static friction is the one that's on act, because kinetic is in motion, static is not. And gravity is actually acting in two directions, right? Gravity is acting into the incline, but also down the incline. And since this force is down the incline, we know static friction must be up the incline. It's opposing the intended motion. Okay, so there's my free body diagram showing all the forces that are acting on this block. How does this diagram change if the box is sliding down the incline? Well, it doesn't change a whole lot, but if this box is in motion instead of at rest, then instead of this being static friction, it will be kinetic friction. So Fs becomes Fk. And then C, how does the diagram change if the box is sliding up the incline after an initial shove? Well, now that means the velocity is this way. Remember, friction opposes motion. So instead of friction acting up the incline, friction is going to actually act down the incline. So the kinetic frictional force will act in the other direction. Okay, it switches sides. Okay, the next one we'll take a look at is number 7, and that one is sort of a long problem, so we'll probably dedicate the entire next video to it.